Hi, and welcome to my channel. Gravity is the force we rarely think about, yet it is constantly at work, influencing every aspect of our daily lives. It shapes our world in countless ways, from the grand scale of the cosmos to the minute details of our everyday existence. It keeps our feet planted firmly on the ground, allowing us to walk, run, and live our lives with a sense of stability. It guides the planets around the sun in a cosmic dance that has spanned billions of years, ensuring the stability of our solar system. Without gravity, our universe would be a vastly different place, lacking the structure and order we observe today. From the moment we take our first steps, we learn to navigate the world under gravity's influence, adapting our movements to its pull. We throw a ball, and it curves back down to Earth, a simple yet profound demonstration of gravity's ever-present force. We jump, and we are inevitably drawn back to the ground, a reminder of gravity's inescapable grip on our bodies. But gravity is much more than just an everyday force. It is a key player in the grand tapestry of the universe. It is one of the fundamental forces of the universe, responsible for the formation of stars, galaxies, and even black holes, shaping the very fabric of space and time. Join me on a journey as we explore the fascinating world of gravity, from its humble beginnings in Newton's orchard to Einstein's mind-bending theories, and discover how this unseen force continues to shape our understanding of the cosmos.
In the simplest terms, gravity is a force of attraction. It's like an invisible bond that pulls objects with mass towards each other. The more massive an object, the stronger its gravitational pull. Think of the Earth, for example. It's a massive object, and that's why we feel a strong gravitational pull towards it. This pull is what keeps us grounded and prevents us from floating off into space. But gravity doesn't just affect us here on Earth. It's a universal force, meaning it affects everything in the cosmos. It's the glue that holds galaxies together and the reason why planets orbit stars. Gravity is everywhere, and its influence is felt throughout the universe.
Our understanding of gravity has evolved over centuries, with many brilliant minds contributing to our knowledge. But the story of gravity is often linked to one name, Sir Isaac Newton. Legend has it that Newton had a breakthrough moment while sitting under an apple tree. He saw an apple fall to the ground and began to wonder what force caused it to fall. Why didn't it go up or sideways?
This simple observation sparked a revolution in scientific thought. I realized that the same force that pulled the apple to the ground also governed the motion of the moon around the Earth and the planets around the sun.
Newton's insights led him to formulate his law of universal gravitation. This law states that every object in the universe attracts every other object with a force proportional to their masses and inversely proportional to the square of the distance between them. In simpler terms, this means that the heavier the objects, the stronger the gravitational attraction between them, and the farther apart they are, the weaker the attraction. Newton's law of gravity was a groundbreaking achievement. It provided a mathematical framework for understanding the motion of celestial bodies and helped to explain a wide range of phenomena, from the tides to the orbits of comets. Section 5. Einstein's universe. Newton's law of gravity worked remarkably well for centuries, providing a solid foundation for understanding the forces that govern our world. However, in the early 20th century, a new revolution in physics emerged, spearheaded by a young and brilliant physicist named Albert Einstein. His ideas would forever change our understanding of the universe. Einstein's theory of relativity, published in 1915, offered a radically different view of gravity. This groundbreaking theory challenged the long-standing Newtonian perspective and introduced concepts that were both revolutionary and profound. While Newton saw gravity as a force acting across space, Einstein proposed that it was not a force at all. Instead, he envisioned a more intricate and elegant explanation for the phenomenon that governs the motion of planets and stars. Instead, he suggested that it was a consequence of the curvature of spacetime. This idea was both simple and complex, offering a new way to understand how massive objects influence the space around them. Imagine a bowling ball placed on a trampoline. The ball creates a dip in the trampoline's surface, altering the way other objects move around it. The ball creates a dip in the trampoline's surface, much like massive objects create a curvature in space-time. This curvature affects the path of other objects, guiding them along curved trajectories. This curvature is what we experience as gravity. It is a subtle yet powerful force, shaping the very fabric of our universe and influencing everything from the orbits of planets to the flow of time itself.
Section 6. Bending space and time. According to Einstein, objects with mass don't simply attract each other through an invisible force. Instead, they warp the fabric of space-time around them. Imagine rolling a marble across the trampoline near the bowling ball. The marble's path will curve as it approaches the bowling ball, not because of any direct force, but because the trampoline itself is curved. This is how Einstein explained gravity. The Earth orbits the Sun not because of a mysterious force pulling it inward, but because the Sun's mass curves space-time, creating a path that the Earth follows.
Section 7. Black holes, gravity's ultimate triumph. Einstein's theory of general relativity made some startling predictions, one of the most intriguing being the existence of black holes. Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape their grasp. They are formed when massive stars collapse at the end of their lives, compressing their mass into an infinitely small point called a singularity. The gravitational pull of a black hole is so intense that it distorts the fabric of space-time in extreme ways. Time slows down as you approach a black hole, and light itself is bent and warped by its immense gravity.
Section 8. Gravitational waves, ripples in space-time. Another remarkable prediction of Einstein's theory was the existence of gravitational waves. Imagine tossing a stone into a pond. The stone creates ripples that spread outward through the water. Similarly, when massive objects accelerate or collide in space, they create ripples in space-time known as gravitational waves. These waves travel at the speed of light, carrying energy and information about the events that created them. In 2015, scientists made the groundbreaking discovery of gravitational waves, confirming Einstein's prediction and ushering in a new era of astronomy. Section 9. Gravity, a tale of two theories. So we have two theories of gravity, Newton's classical theory and Einstein's theory of general relativity. Which one is right? This question has intrigued scientists and philosophers for centuries. The answer, as is often the case in science, is that both theories are correct within their own domains. Each theory has its own strengths and limitations, and they complement each other in our understanding of the universe. Newton's law of gravity works remarkably well for most everyday phenomena, and even for predicting the motion of planets in our solar system. His equations are simple and powerful, making them incredibly useful for a wide range of applications, from engineering to space travel. However, Einstein's theory of general relativity provides a more complete and accurate description of gravity, especially in extreme environments like black holes and neutron stars. Einstein's equations are more complex, but they reveal the true nature of gravity as the curvature of space-time. It also explains some phenomena that Newton's theory cannot, such as the bending of starlight by gravity and the existence of gravitational waves. These discoveries have opened up new frontiers in astrophysics, allowing us to explore the universe in ways that were previously unimaginable. Both theories have been instrumental in advancing our knowledge, and together they provide a more comprehensive picture of the cosmos. As we continue to explore and learn, who knows what new theories and discoveries await us in the future? Section 10. The future of gravity research. Despite centuries of study, gravity remains one of the most mysterious and least understood forces in the universe. Scientists are still working to unify gravity with the other fundamental forces of nature: electromagnetism, the weak nuclear force, and the strong nuclear force. This quest for a unified theory of everything is one of the greatest challenges in modern physics. If successful, it could revolutionize our understanding of the cosmos and potentially unlock new technologies we can only dream of today.
Section 11. Conclusion: gravity's enduring influence. From the apple that fell from a tree to the ripples in space-time, gravity has captivated the imagination of scientists and dreamers alike for centuries. It is the force that shapes our universe, from the largest galaxies to the smallest particles. As we continue to explore the cosmos and delve deeper into the mysteries of gravity, we will undoubtedly make even more groundbreaking discoveries that will reshape our understanding of the universe and our place within it.